Welcome back. Having done the theoretical process calculations, I will now show you how we implemented the process in practice, from lab to plant. First, the yeast had to be genetically modified to be able to produce sufficient succinic acid. A metabolic pathway was introduced to establish the highest possible yield. After a quality check, if the pathway was successfully integrated, we did a first production test on a mica titer plate with limited control on the fermentation conditions. With the help of an automated system, many different strains could be screened at the same time to select the best performing organism in relation to succinic acid production. It is at this stage that we obtained a first indication of how the organism was going to perform. The best transformants we subsequently evaluated in a controlled environment in the lab fermenter. This setup is a representative downscale of the final targeted fermentation volume in a commercial plant. Hereafter, the process was further scaled up from 10 liter to 1 cubic meters to 100 cubic meters in our demonstration plant. The following graphs show the results that we realized during the scale-up and improvement of the process. The first results we obtained from the mica titer plate have around 10 grams per kilogram succinic acid, but still an excess of byproducts was produced, which is unfavorable. When we evaluate this strain in a controlled environment, called the fermenter, we could already enhance the performance for succinic acid by a factor 3. Now you can see that we have more succinic acid than byproducts, but still the byproduct levels are too high to have an economical viable process. After that, we did quite some improvements in strain engineering and process conditions. Typical results we're having now is that we can reach product concentrations of around 100 grams per kilogram at pH 3 and almost no byproducts formed, meaning this process is ready for implementation in a plant. We also looked at the feasibility of the application of cell recycle, as explained during the previous unit. This graph shows that the recycled yeast has a similar productivity as seen in the first fermentation. This was also seen after multiple recycles, which is very promising. So if we then quantify what the impact is of having multiple recycles on our overall performance, we can see that having the first recycle really gives the most added value. But we can also see that every extra recycle gives a lower additional improvement. This illustrated for us that we only need a limited amount of recycles to have the overall best performance, and with that also minimize the risk for contamination. Looking at the history and the future of our manufacturing plan, we started our first pilot test in 2008 and moved in 2010 to a demonstration plant, which we really operated as a plant. The purpose of that plant was to demonstrate the technology we developed and also to deliver tons of representative material to our customers. End of 2012, we started our first commercial plant with an annual capacity of around 10 kiloton. This plant is located in Italy on the site of our partner Roquette. As feedstock, we are using starch hydrolysis, and we fully integrate here with the existing starch hydrolysis production process of Roquette on the same site. And by doing that, we reduce the costs and realize and improve sustainability. As we developed this process ourselves from scratch, we also filed quite some patents to protect our technology position, most of them related to the strain and the process. To conclude, I would like to give you some take-home messages to learn from this case study. First of all, we demonstrated that an improved sustainability and production cost decrease do not necessarily have to be competing. The example of low pH fermentation showed that the lower amount of titrant requirement decreased both CAPEX and OPEX, but also decreased waste treatment and energy costs. Another important lesson is that yield, productivity and titer are influenced by different factors, but do not necessarily operate independently. A third lesson that I would like to emphasize is the potential advantage of cell recycle for fermentation costs. So explore the feasibility of this for your process. And finally, I hope I could convince you to do some calculations to determine your ideal process before actually starting your process development work. See you next time.